Welcome to module 1, lecture 3. We shall be starting from where we have stopped, that is bonding action. Then we shall look into heat of hydration and compound contribution to strength. Then we will look into degree of hydration, followed by hardened paste structure models, and obviously from that we will calculate out porosity. Now, last class we were mentioning that CHS gel has large specific surface. It has a gelatinous structure and large specific surface, and the order of this specific surface is 1000 times more than that of the cement. You can see that it is 223 into 10 to the power 6 centimeter square per gram compared to that of cement, which has 2.25 or 4 into 10 to the power 3. The surface forces therefore will dominate, because the surface area is so large, surface forces will dominate. Now, and just as an example, one can think of, say, if I have large size particle like stones, they are not bonded. Stones you can separate out very easily. Sand, well, you can separate out quite easily. Come to clay, the surface area is very large, because particles are small. We shall see that surface area is inversely proportional to specific surface area per unit volume. If I say, it will be inversely proportional to the particle diameter. So, if my particle diameters become smaller, specific surface becomes large. So, in case of clay, specific surface is very large, therefore, you can't separate clay out, they stick together. Cement gel is very fine gelatinous particle, and therefore, very large surface area. Like clay, the intermolecular forces tend to hold them together. So, surface forces which are intermolecular in nature, they are intermolecular in nature, they are of the order of around 7 MPa, are responsible for cementing action of gel to gel. So, you can't separate out gel from gel, because there are intermolecular forces. These intermolecular forces, what are they? The intermolecular forces are the force that act between stable molecules or functional groups, or between functional groups of macromolecules. So, they act between molecules or functional groups. Electrovalent or covalent bonds are between atoms to form the molecule. These forces acts between the molecule, they put the molecule together, they act between the molecule. So, bonding action between the molecule, those are the intermolecular forces. And in cement gel, these intermolecular forces held gel with gel together. The weakest of these intermolecular forces are van der Waals forces. Weakest of these intermolecular forces are van der Waals forces. They are also known as London dispersion forces. Essentially, they include momentary attraction between molecules, diatomic free elements and individual atoms. So, that is momentary attractions, right. They essentially differ, from covalent and ionic bonding, which are between atoms whereby either charge transfer takes place or sharing of electron takes place, that is essentially electron transfer takes place or sharing of electron occurs. That is for between atoms to form compounds. Now, these are or to form molecules. Now, these ones are intermolecular forces. So, they differ from those covalent and ionic bonding, because these are not stable bonds and are caused by momentary polarization of particles, momentary polarization. So, van der Waals bonds, thus residual bonds result from separation of electric charges. So, electric charges which get separated, they form residual bond because of the separation of electric charges. In many covalent molecules, the outer shell electrons are shared, and therefore, the charges, the center of positive and negative charges, they may not coincide, form dipole, and this may result in kind of bonding forces between molecules, and these are the forces which are responsible. Similar forces are responsible for bonding gel to gel. For example, in case of gas molecule like hydrogen H2, there are 2 H atoms or oxygen, etc. Electron in the covalent bond of H and H, electron in the covalent bond of H and H are concentrated in the bond direction, and resultant positive and negative charges separation occurs. So, along the direction of the bond, electrons are concentrated, thus dipole is formed. So, that is what is, wherever dipole is formed, you might find intermolecular forces or van der Waals forces acting. Bond with hydrocarbons is covalent, that is between say carbon to carbon in a hydrocarbon, these are covalent, right. But between adjacent hydrocarbons, the bonds are van der Waals type. For example, if you have carbon carbon chains, these are all covalent bonds, but if I have 2 such chains, in polymers fibers for example, in that case the bond between these two would be intermolecular type, like the van der Waals bond. So, they are bonded by this kind of action, they are bonded by weak forces. So, CHS gel has got this sort of bond, which are not strong chemical bond, but van der Waals kinds of bond, and gel to gel separation requires breaking those van der Waals bond, right. Many other materials do not have any bond at all. For example, sand particles, between sand particles there are no forces of attraction which are holding them together, or stones, large surface area, small surface area compared per unit mass or per unit volume, the forces do not act, right. So, these van der Waals bonds are mechanically very weak and they are elastically deformable, exhibit poor conductivity of the resulting material. So, the material where the van der Waals bonds are there, they are elastically, that means, if you apply load, they will deform and may come back to its original position, and they have poor conductivity, and CHS gel will be like that. Generally, CHS gel is stable in water. Now, van der Waals bond or 7 MPa intermolecular forces cannot be the only force which is bonding them, but by and large this is the force. So, stability of hardened paste in water indicates there is something more than just 7 MPa intermolecular forces which holds them, but nevertheless that is the major cause or major force understood to have been responsible for strength of gel to gel. Structure of gel is essentially thin sheets 15 to 100 nanometer layers thick, that is what it is. We will have a diagram, people have actually determined by some tests, and their structure, these are thin sheet like structures 15 to 100 nanometer layer thick. So, this has been determined by various indirect tests. Now, proximity of the surface atom can also give rise to chemical bonding of O calcium oxide to oxygen. So, the surface atoms can form bond between gel layers, because that is the explanation that 7 MPa cannot be just the only thing, because it is stable in water, which means that there is something more than simply 7 MPa. And one of the ideas suggested is that between surface, calcium, oxygen to oxygen bonding might be there, between gel to gel sheets, right, gel to gel sheets, this bonding may also be present because of the surface atoms, which, right, or hydrogen bonding, or by condensation of silicon hydroxyl tetra, OH4 groups leading to Si linkages. So, other kind of chemical bonding is also thought to be responsible for bond between gel to gel, in addition to the van der Waals bond, because it is stable in water. So, gel to gel bond is van der Waals kind, or some sort of chemical bonding also may be present, and that is what results in strength of gel. Well, if the tension is applied, these forces will oppose the tensile force. So, separation will be opposed by these forces which are bonding the gels. Compression on the other hand, is restricted by covalent bond within CHS. So, you try to push them. Now, you are pushing the sheet against one sheet against another. If you are trying to push them, you are pushing one sheet against another. If you are trying to push the sheets CHS under compression, you are actually pushing one sheet against another, which means that you are trying to compress the CHS gel itself, CHS bond itself, which is not possible. So, that is why they are strong in compression, because you can't compress CSH bond so easily, but if you pull, it would be, you can separate out the sheets or CHS from one to another. Only the forces responsible for their bonding, that is of the intermolecular forces, they will hold them together. So, they are weak in tension, because it is intermolecular forces opposes the tensile force, whereas covalent bond in CHS opposes the compressive forces, right. So, they are much stronger, and they are 100 times stronger than this compressive forces are 100 times, compressive the bond under compression, the bond that has to be the bond, the force restricting the compression or is 100 times more than van der Waals bond. That is why they are so strong in compression. Well, bond with aggregate is essentially mechanical interlocks. So, we will come to that sometime later on. Bond with aggregate is mechanical interlocks. Let us see. So, first of all, van der Waals forces opposes the forces under tension or intermolecular forces of all kind. Compression is restricted by covalent bond within CHS, and that is 100 times more than van der Waals bond. So, therefore, they are strong in compression, not so strong in tension, and of course, when it comes to aggregate. So, it is gel to gel to aggregate is of course mechanical interlocks, right. Gel to gel is mechanical interlocks, right. So, that was the bonding action. Why cement can bond itself, cement paste, you can't separate out cement paste itself, that is the reason. But their bonding with aggregates of course is mechanical interlocks. We will look into it sometime later on when we look into the concrete strength. Next, we look into heat of hydration with time. Let us see heat of, because we have seen the contribution of each compound of cement to heat of hydration, but with time how the heat of hydration is evolved. Let us look at it. This side is time in hours, let us say, and that side is rate of heat evolution, Well, initial phase is of course in minutes, then in hours, then in days. Now, if you look at it, this is how the heat of hydration would look like. You have a peak right in the beginning, quick initial dissolution period, followed by rate gets reduced down, then rate picks up again, and then the small hump here, and that it follows that way. So, the stages I can say first is stage 0, followed by stage 1, stage 2, 3 and 4 and 5. First 0 stage is initial dissolution. So, at that stage there is quite a bit of heat evolution, rate of heat evolution is high. Then in the stage 1, dormant, it will relate to a dormant period. C3s hydration occurs here when rate of heat evolution of heat is pretty high, and C3 hydration occurs late stage. So, in this stages 1, we will see that it is ettringite formation, 2 CHS growth, 3 and 4 is also CHS growth, and 5 is further CHS growth. So, this stage initial CHS growth occurs. This is initial dissolution period. Stage 1 is ettringite formation, stage 1 is ettringite formation, stage 2 is some CHS growth, 3 and 4 CHS growth, and 5 is again CHS growth. C3s hydration occurs at the peak. When the heat of hydration is peak, C3s hydration occurs, and next level of C3 hydration that occurs later on, that gives another small hump. So, that is heat of hydration, rate of heat evolution. You can see rate of heat evolution, that is heat evolution per unit time, that is what we are looking at, joules per gram per hour if we look at it. Now, total heat evolution if we look at it, that would again with the same time. So, majority of the heat evolution really takes place in the initial this 20 hours or so, and the order is of the total order would be 320 joules per gram, etcetera, after complete 24 hours or so. So, peak heat of rate of heat evolution will be 4 to 6 hours, as we have seen in the last summer here, about 7-8 hours, 10 hours at that time, and after that it becomes stabilizes out. So, initial there is a peak, but that is not a small period. So, if you sum it up, it is not very large, but then therefore, there will be rate of heat evolution will increase and attains a peak somewhere there at this stage, and after that rate of heat evolution reduces. So, total heat evolution also reduces. Total heat, of course, you can find out from Q1, that is the heat of hydration of C3s multiplied by the amount of C3s. Q2 is the heat of hydration of C2s multiplied by the quantity of C2s per unit mass. Q3 is C3a, heat of evolution of C3a, and the amount of C3a per unit mass in the cement. Q4 is the heat of hydration of C4AF, and this is the quantity. So, you can sum this up to find out total heat evolution at any stage or even in totality complete heat of hydration. This this quantity we know, and this I have given you earlier sometime, the quantity of heat that is liberated per unit mass from the C3s and similarly from C2s, C3a and C4AF. The another important aspect is strength contribution. So, we have seen that actually C3s hydration takes place in the beginning when we looked at the when we earlier looked into the various phases that is formed or various product that is formed with time, and we have seen that it is first the ettringite reaction followed by formation of CHS after about 6 hours or so, and then calcium hydroxide also comes out. In this case actually C3s reacts earlier, C2s reacts late. So, therefore, strength development if we see C3s is responsible for early strength development, C2s initially does not, rate of strength development is not much, right. It follows like this, and C3a contribution to strength is less and C4AF contribution to strength is even less. So, initial strength normally comes out within 7 days, because we are talking of days would be from C3s. 28 days C2S contributes, but it do contribute significantly to long term strength. But you see, if you see C3S after about 28 days, hardly any strength, the rate of strength gain has reduced significantly for C3S. On the other hand, C2S picks up here, the rate is increasing, and so long term strength comes from C2S, long term RD strength. This has got less strength contribution. So, the strength contribution was, it is C3S which gives RD strength, C2S gives later strength, and we have seen that is because the CHS that would come initially in the beginning would come from C3S, and later on only C2S reaction takes place. Okay. We define the term degree of hydration. Degree of hydration is the fraction of mass hydrated at any time. In our case, we are denoting it by H. So, degree of hydration, H is the fraction of mass hydrated at any time. That means, well, just for our understanding, if C dash is the mass of cement hydrated, C is the original mass. So, H is given by this. So, mass hydrated, quantity of cement hydrated divided by original. So, therefore, H is a fraction, it is a fraction. So, H is expressed, degree of hydration is expressed as a fraction, it is the fraction of mass hydrated at any time, and this is a function of time. This is a function of time, and as you can see, with age, degree of hydration increases and then tends to become steady. As we have seen, because cement consists of 4 major compounds, C2S, C3S, etc. So, they will, a portion of it will hydrate up to certain period of time, and later on the hydration rate is, strength development is slow. So, naturally hydration is also slow. So, it picks up. So, it is typically of this kind of curve, but recently this a few more measurements, that experiments, many recent experiments have demonstrated that this degree of hydration is a function of water cement ratio as well. Even for water cement ratio, high water cement ratio like 0.5, 4, 0.5, 0.6, etc., it is a function of water cement ratio itself. And one can measure this from non evaporable water content. So, you take the cement paste at any age, under controlled condition you have prepared the paste, continuous hydration, and then block the hydration by some treatment. Actually, isopropyl alcohol, if you put it on, that will absorb all water and stop the hydration. So, at any age you can stop the hydration, then you can heat it up to find out the non evaporable water content. Evaporable water content will go away at 110 degrees centigrade, but after that if you heat up, you can find out the non evaporable water content, and from that non evaporable water content measurement one can find out what is the degree of hydration, and one can possibly relate this to the water cement ratio, that age in this manner. So, it is a function of log of age, also function of log of water cement ratio, and these coefficients are of the order of around k 1 is 0.2 of the order, k 2 is 0.06, k 3 is around 0.6 or so. I think this so this one can obtain these constants from actual measurements. So, some values are available in literature and one can find these values, right. So, that is degree of hydration. Now, let us look at structure of CHS structure. Now, several models have been proposed. This one is proposed by Ishai. These are sheets. So, you have got sheet, one sheet, another sheet and the other sheets. So, this sheet like structures having thickness of order around 30 Armstrong. This is 400 to 600 Armstrong sheet length, and the space in between is 20 to 40 micron interlayer this space, interlayer space. So, and the water is there. Now, in porous material water can be held. In porous material you can hold the water. First is chemically bound water, that we have seen, chemically bound water, and chemically bound water are the CSH. So, this is chemically bound, that we have seen. Then besides that, since the surfaces can have intermolecular forces, there may be polarities. So, water being H2O being a polar liquid, it has got a dipole. So, center of positive charge and negative charge, they may not be at the same point, they may not be coinciding. So, therefore, it is polar. So, it can get adsorbed at the surface. So, you have got adsorbed water at the surface, adsorbed water, right, adsorbed water. Now, between two layers, he actually called it intercrystal water, between two layers. So, other than chemically combined water, of course, you can have adsorbed layer, adsorbed water. And besides that, of course, you can have capillary water, which is taken up by suction, capillary suction, right. If you have larger size pores, or relatively some mesopores, not very small pores, fine particles, they of course adsorbed layer would be there, but slightly larger size pores, water can penetrate by capillary suction. So, the third type of water held is capillary water, and in some cases there can be water held simply by mechanical action. For example, if I have a pore like this, here water comes in, here water comes in, and water comes in and it is just stuck here. So, this is mechanically held water. Now, in concrete or cement paste, you will have chemically bound water, adsorbed water, and capillary water can also be there if it is saturated. All right. Now, in his model, in the model he is talking of these sheets, adsorbed water are, they form layer of water at the surface, and the density is not 1, density of this water is not 1, right, it has got a different density. So, the adsorbed layer will be somewhere there at the boundaries at the surface. Then this water he is calling intercrystal water, which is between the layers of CHS, and then still there will be some water between the space between the sheets, it is being called as gel water, gelled water. So, this was the model proposed, one model proposed. There is another model after Shreda, and here you can see is adsorbed water again at the surface, and these are the sheets. So, CHS sheets are here, the adsorbed water at the surface, interparticle bond is between this particle and another sheet, adsorbed water, these are the sheets. So, they are not in exact layers, parallel layers, but they are in different orientation. This X cross are interlayer hydrate water. So, interlayer hydrate water is in the shown as cross. So, these are all interlayer water, adsorbed water is here, these are the layers, and within the layer there is interlayer water, right. So, interparticle bond is here, adsorbed water, CHS sheet, A is this interlayer water, and these are the CHS sheet, B is interlayer hydrate water. So, this is another model, and this is the model proposed by Power. In this model, these are the CHS sheets you can see, and capillary pores. There are large space which he calls as capillary pores, as I was telling you, where relatively larger pores. This ones water can enter by capillary suction, right, following because of the surface tension forces. Because of the surface tension forces, as you know, at the interface there will be surface tension forces, like you dip a capillary. If you dip a capillary into water, there is capillary rise, as you know, capillary rise, and this is because of surface tension forces. So, water can come here because of surface tension forces, and these pore sizes are large, and these are called capillary pores, and gel pores are smaller ones between the gels. So, these are the CHS sheets, and this between the CHS sheets, the space which is there where there will be gel pores, gels, this he calls as gel pores, which is inherent of the gel system. Now, larger pores are capillary pores. So, this is how the Powers model looks like. We have capillary pores and layers of CHS, and within the layers of CHS, the smaller pores are being called as gel pores. So, these are the models which represents the hardened paste structures. Okay. So, having done that, now we can think of pores in the paste. Gel is as we have explained earlier, gel is colloid sized particles having 28% characteristic porosity, involving pores of average width as 15 angstrom, and these are gel pores. So, they are gel pores are micropores, or you can say even nanopores, 0.5 nanometer to 100 nanometer size. These are generally considered to be responsible for shrinkage and creep. Capillary pores, they are slightly larger size, called mesopores, and size would be 5 nanometer to 5000 nanometer. They are responsible for mechanical strength, that means load carrying capacity and durability property of the cement paste and then concrete. Then there could be pores coming because of pore compaction. So, these are macropores, or because of air entrainment. Air entrainment is deliberate air entrainment is used in some cases in order to provide better freeze thaw resistance. We will look into that sometime later on, and pore compaction can also result in large sized pores. So, therefore, what we see is the cement paste has got a structure, it is porous, inherently porous. Hydraulic cement paste has got a hardened paste has got a structure which is inherently porous, and it has got two types of pores that has been recognized. One is gel pores, it has got a gelatinous structure CHS, that is the major compound which is formed after hydration. It has got a sheet like structures, and it is inherently porous with 28% characteristic porosity. The 28% characteristic porosity has been determined from indirect experimental evidences. Similarly, the size of the gel pores has been also determined from experimental evidences, nitrogen adsorption technique, etc., etc. Then the other type of pores which can be there is the capillary pores, which are large sized pores, and if you recall the hydration process that we looked into, we said that there are inner product of hydration which is within the original grain boundary. We have outer product, because hydration product occupies more volume than the original cement. Therefore, some of those water filled space will be filled in by hydration product, and those we call as outer product. Calcium hydroxide also stays outside the original grain boundary, and originally water filled space which remain vacant after hydration forms capillary pores. So, if you can recall that, we can see that those pores are of the larger size and they are responsible for durability and mechanical properties, namely strength, etc. And larger size pores could be there if we have deliberate air entrainment. Why we do it, we will come to that sometime later on. And if you have a poor compaction, then also you can have large size pores. Let us see how much is the chemically combined water, right. Now, to do that, people have done tests, experiments on individual compounds, right. So, if we want to find out the chemically combined water, all right, we must know how much is the amount of water C3S will require for full hydration, how much the quantity of water C2S require for full hydration. So, this is the quantity of water required by 1 gram of C2S for its full hydration. A3 is the quantity of water required by 1 gram of C3A for full hydration, and AF4, similarly AF4 is the quantity of water required by 1 gram of C4AF for full hydration. So, then this is the chemically combined water. So, chemically combined water per unit mass is Wn is the amount of water that will combine with C, cement. C is the quantity of cement. So, quantity of water that will combine with per unit mass is Wn by C, and if I know the quantity of C3S, proportion of C3S, proportion of C2S, proportion of C3A and proportion of C4AF, then I can find out chemically combined water for C quantity of cement. The compound quantities proportion would be C3S, C2S, etc. Now, people have actually done experiments for very long term experiments have been done by people to find out the amount of water bound to each compound, and these results are actually given in this table. If you look at it, these are AIs, this A1, A2, A3, A4 with a water cement ratio, water to cement ratio and age. So, water cement ratio of 0.4. In 1 year it was observed that 1 gram of C3S consumes around 0.2 to 8 grams of water for 0.4 water cement ratio. 6.5 years this becomes 0.234, and in 13 years this became 0.230. So, complete hydration nearly one can assume 13 years is a very long time, and the tests have been performed on individual compound in this manner. A2 is that was for C2S, and in 1 year 0.168 grams of water reacted with 1 gram of C2S. In 0.4 years, I mean in 6.5 years 0.178, and in 13 years 0.196, all this with 0.4 water cement ratio. Similarly, A3, you can see that in 13 years 0.5 to 2 grams of water reacted with 1 gram of C3A, and A4, that is 1 gram of C4AF reacted with 0.132 grams of water in 1 year. In 6.5 year 0.158, and 13 year it was something like this. But if the water cement ratio changed to 0.6 and 0.8 in 6.5 years, the variation was something like this. I think there may be some mistake in this figure, whatever it is. What we see is that different quantities of water are required by different compounds of cement for their complete hydration, because 13 years one can assume it to be a full hydration. Now, supposing I assume 48% C3S, 25% C2S and 11% C3A and 9% C4AF, chemically combined water at complete hydration is given by this formula 0.23 into 0.48, because 23 into 0.48, because 48% is C3S, 0.25 into 0.196, and 11% C3A. So, it is like this, and approximately this value comes out to be 0.23. So, with 48% C3S, 25% C2S, 11% C3A and 9% C4AF, 100 grams or 1 gram of cement containing this quantity, because 1 gram of cement will have then 0.48 grams of C3S, 0.25 grams of C2S, etc., etc. So, 1 gram of cement will react approximately with 0.23 grams of water. If this proportion changes slightly, this might change a little bit, because that is why I have written approximately. So, generally, supposing you consider this as 55, this as 22 and this is maybe somewhat less, etc., etc., this value will change, but round about 0.23 only, but round about 0.23 only. So, round about 0.23 only. So, values would change approximately, therefore, 1 gram of cement reacts with 0.23 grams of water in for complete hydration. 13 years is a very long time, after that there was practically no hydration. So, stoichiometrically we can say that 1 gram of water, 1 gram of cement requires 0.23 grams of water for complete reaction, all right. Okay. So, this is one information. Another information that became available from early experiments in 1950s is that density of hydration product, solid product of hydration, varies from 2.43 to 2.59, 2.43 to 2.59, and if you look at the average, it will be 2.51 grams per cc. So, 100 grams of cement therefore chemically reacts with 23 grams of water, 1 gram with 0.23. So, 100 gram with 23 gram of water, and would it produce 1.23 gram of hydration product, which can occupy 1.23 divided by 2.51, 0.49 cc, because this is grams per cc, this is the grams. So, 0.49 cc. So, the hydration solid product of hydration will occupy 0.49 cc, right. Now, if you look at cement, its specific gravity is generally taken to be 3.15 on an average. So, 1 gram of cement will occupy 1 by 3.15, that is 0.32. This will come out as 0.32. So, 0.32 plus 0.323, and water occupies the same volume, sums up to 0.55, and that is 0.55, and the product solid product of hydration occupies 0.49. Therefore, this occupies less than the original volume of water, right, original material. This is assumed to be some empty space. So, the difference is assumed to be some empty space. You see, this difference is assumed to be, so 0.32 plus 0.23 makes it 0.55, this is what it is, minus 0.49 gives you 0.06 cc, and therefore, this is assumed to be some empty space. But this 0.49 actually has got internal pores, and this is typically 28%. So, it has got internal pores 28%, 0.06 cc of water remains aside, but this 0.49 actually will occupy much higher than 0.49, because 28% characteristic porosity is there, 28% characteristics porosity is there, and therefore, 0.49 divided by 0.72, which will give you roughly about 0.68, and therefore, this difference gives you 0.19 cc. So, the gel porosity is 0.19 cc, gel porosity is 0.19 cc, or I mean gel pores is 0.19 cc. So, if I take 1 gram of cement, if I take 1 gram of cement and allow it to hydrate fully, then it will occupy actually 0.49 cc, the solid product of hydration will occupy, 0.19 cc will be occupied by the gel pores within enclosed within this product of hydration, plus you may have a capillary pore space of 0.06 cc, empty capillary sized pores. So, this is what comes from the previous models. And if I consider C gram of cement mixed with W gram of water, the volume would be C divided by 3.15 plus W. So, 0.332 C plus W, 0.32 C plus W, 0.32 C plus W, right, because specific gravity or density of cement is taken to be 3.15 grams per cc. After a period of hydration, say degree of hydration being H, Ch gram of cement would react, because H is defined as a fraction, with 0.23 Ch gram of water to produce 1.23 Ch gram of hydration product. The volume occupied by the solid product of hydration therefore is 0.49 cc. So, this is cc, basically 0.49 cc. Same calculation follows, because 1.23 grams occupied 0.49, Ch is the amount of cement that is reacted. So, therefore, 0.49 Ch. Gel porosity is 28%, thus volume of gel pores would be 0.19 Ch. Same thing, same calculation is being repeated, only now I add Ch with it. So, earlier everything was 1 gram I was taking. If I take C grams of cement and H is the degree of hydration, then Ch grams of cement will react and everything has to be multiplied by Ch, and that is how I get it. So, I get 0.49 Ch as the solid per volume of solid product of hydration, 49 Ch cc, 0.19 Ch cc is the gel pores volume, right. So, that is how I can just calculate out the volume of pores, gel pores. The mass of unhydrated cement of course, will be C into 1 minus H, mass of, because Ch has hydrated originally C minus Ch is nothing but C minus 1 minus H. So, that is what it is. Mass of unhydrated cement will be only this much, and corresponding volume, because density of cement is 3.15. So, will be 0.32 C, this should be bracket C H, 0.32 C into 1 minus H, into this should be bracket 1 minus H, 0.32 C 1 minus H, that would be the mass of volume of unhydrated cement, volume of unhydrated cement, and volume of empty capillaries will be same 0.06 Ch, like earlier we have done, it will be 0.06 Ch. Now, reaction takes place, it takes time, it does not occur instantaneously, it is not instantaneous, but the framework of the solid is formed quite quickly. So, within half an hour time, initial set. So, framework forms pretty quickly, you can't disturb it any further. So, solid skeleton is formed within a short time. Since solid skeleton is formed within a short time, the rest of the hydration product occupies only the space available within that solid skeleton. So, additional hydration product occupies original water filled space within the skeleton. The structure is formed very quickly, this is the structure formed, but some space are blanked. So, those blank spaces are filled in by additional hydration product, because solid is formed, but a porous solid structure is formed once it solidifies, and those porous, remember we had blue colored water which outer product filled in, leaving some water filled space. Those space are the space available for hydration product those are generated in the later stages of hydration, because solid skeleton is formed within a short period of time, and the force of hydration, the volume expansion force of hydration is not so high as to cause disruption of the structure. Therefore, they only fill in the original space, there will be no change in the total volume. So, this if we look into this, we look into it will look like this is schematically cement C grams, water W gram, time let us say hydration has occurred, degree of hydration let us say is H. Now, unhydrated cement remaining is C into 1 minus H gram, and its volume is, well, this is 3.32 I will say 32 C 1 minus H cc approximately, and this is the unhydrated volume. This is the solid hydration product which is 0.49 CH cc, that is what we have seen. This will be the gel pores, corresponding gel pores which is 0.19 CH cc, and some space of water still not filled by the material remain as capillaries. We can call it as capillary water. And empty capillaries will be like this. So, this is the empty capillaries, and this sums up whatever we have discussed. Now, original volume is this much, how much? 0.32 C plus W cc, and this volume is conserved. So, this volume must be same as this volume. This volume is conserved. So, therefore, this volume must be same as this volume. Therefore, using these concepts, I can calculate out the porosity. So, porosity of paste I can calculate out. The volume is conserved. The volume of capillary water will be total initial volume minus volume unhydrated cement and empty capillaries. I can just find out the capillary water volume by finding initial total volume is known and other component volumes are known, I subtract them. We will look into this in the next class in the beginning, the equations etc., and we will find out that the volume of capillaries, empty capillaries would work out to be W minus 0.36 H. Therefore, porosity I can calculate out, get an expression for the porosity based on this. We will repeat this in the next class, and gel porosity I can find out total porosity. So, this we will look in the next class. So, summarizing, today we have looked into bonding action, heat of hydration, degree of hydration, structure of hydrated paste, and we try to find out the porosity, which we shall be looking into in the next class. So, that is what. So, next class we will look into the total porosity and followed by properties, tests and various kind of properties of cement paste. Thank you very much.